Welcome to Lecture 13. We'll still be working on Karnaugh maps in this lecture. And so let's jump in right away with an example. This one will be, as you'll see, a little bit different from some of the previous ones. We'll say find all minimal sums for f of w, x, y, z equals the sum of the minterms 0, 4, 5, 10, 11, 13, and 15. I would encourage you to stop the video at this point and to try to work this problem on your own, because this one is a little bit tricky, and if you can get this problem completely correct on your own, then I think that you understand the topic of using Karnaugh maps to find minimal sums. And after this problem, we'll go to the topic of using Karnaugh maps to find minimal products. But again, if you think you can do so, I would encourage you to give this problem a shot before returning to the video and seeing it worked out in detail. Okay, so now to in fact work it out in detail, as usual, we begin by looking at the number of independent variables, which in this case is 4, and therefore the number of cells in our Karnaugh map will be 2 to the 4th power, or 16. So this is one of those cases where we will have a 4x4 Karnaugh map. On the vertical axis, we will have W and X. On the horizontal axis, Y and Z. And again, the way we choose those is we look at the order in which the variables are listed here in the argument of the function. And so since W and X are first, we put those on the vertical axis. Since Y and Z are last, they will be on the horizontal axis. And then we number these in the usual way. And filling in the Karnaugh map, I hope, is easy for you now. You'll just go through counting the cells. So the first cell here is 0, and since 0 is one of the minterms for this function, we get a 1 there. But we don't have minterm 1, so we leave that blank. We don't have minterm 2, so we leave that blank. We don't have minterm 3, so we leave this blank. We do have minterm 4, so we put a 1 here. We do have minterm 5, but we don't have 6. We don't have 7. Now remember, for 8, you need to skip down to here, in the lower left-hand corner. We don't have 8. We don't have 9, but we do have 10, and we do have 11. And now finally for 12, minterm 12 corresponds to this cell. We don't have minterm 12, so we leave it blank. We do have minterm 13, then skip over. We don't have 14, but we do have 15. And so this would be the Karnaugh map for this function. Now we want to identify the prime implicants. Clearly we don't have any rectangular groupings of 16 one cells, which is the largest possible, of course, in this case. because we don't have 16 one cells. In fact, we have 1, 2, 3, 4, 5, 6, only 7 one cells. And so that tells us also that we won't have any rectangular groupings of 8 1 cells, again because we simply don't have 8 1 cells. What about now going down to the next power of 2, which is 4? Do we have any rectangular groupings of 4 1 cells? And the answer again is no. What about rectangular groupings of 2 1 cells? Well, yes, we have plenty of those, and so let's take a look at it. First of all, you might ask yourself, do we have any tricky ones? And I don't believe that we do have any that start on one side of the Karnaugh map and are continued to the other side of the Karnaugh map, so we just look at the obvious ones. Well, we'll start up here. We have that grouping. And if we now ask ourselves, well, what will be the name for this? We see that W is constant and equal to 0, so W prime will be part of the name. X is changing because X is equal to 0 in this first cell and 1 in the second cell, so X will not appear. Y and Z are both constant and equal to 0, so we have Y prime, Z prime. And that will be the name for that prime implicant. Now the next prime implicant that we see will be this one. So let's try to find the name for it. And once again, remember that these little sketches that I'm including above the prime implicant are simply for convenience. If you don't want to use them, you don't have to. And certainly, even if you do use them, don't take much time trying to make them very neat. They're just to help you remember where on the Karnaugh map the prime implicant under consideration falls. So for this prime implicant, we see that W, since this is a horizontal grouping, W and X are both constant. W is constant equal to 0, X is constant equal to 1, so we have W prime X as part of the name. And now we ask ourselves, well, what about Y and Z? Well, Y is equal to 0 in both of these cells, so we have Y prime, but Z is 0 in the first cell, and Z is equal to 1 in the second cell. So since Z is changing within the prime implicant, it does not appear in the name. And so this prime implicant that we've just identified is W prime X Y prime. And now we go to the next one, which would be this. And now we have to figure out the name for that. Notice that in these two cells, we note that W is equal to 0 in the top cell and 1 in the second cell. So since W is changing, it does not appear in the name. X is constant and equal to 1, so we have X. Likewise, since this is a vertically arranged grouping, Y and Z will both be constant. Y will be constant equal to 0, Z will be constant equal to 1, so we have Y prime Z. And so the name of that prime implicant is X, Y prime Z. And now we go to the next one, which is this. What about this grouping? What's the name? Well, since it's a horizontally arranged grouping, W and X are both constant. W is constant and equal to 1 for these two cells. X is constant and equal to 1 for these two cells. So part of the name is WX. And now as we look at the Y and Z axis, Y is changing, is equal to 0 in this cell, but it's equal to 1 in this cell. And so since Y is changing, it does not appear in the name. Z is constant and equal to 1, so we have Z. And now the next prime implicant, right here. We note that and as we begin to look at for the name for this prime implicant, W is constant and equal to 1. So we have W. X is changing. It's equal to 1 in the top cell and 0 in the second cell. And therefore, since X is changing, it does not appear in the name of the prime implicant. Y and Z are both constant for these two cells. And so both Y and Z will appear in the name. And in fact, since Y is equal to 1 and Z is equal to 1, it'll be Y and Z. There won't be any complements. So W, Y, Z will be the name of that prime implicant. And then we have one more prime implicant down here in the lower right hand corner. And for that one, we see, as we begin to try to name it, we see that W is constant equal to 1, X is constant equal to 0. So we have W, X prime. And Y is constant and equal to 1, but Z is changing, is equal to 1 in this cell and 0 in this cell. So Z does not appear in the name. Y is constant equal to 1, so we have a Y. And therefore, the name of that prime implicant is WX prime Y. And that finishes up all of the prime implicants of size 2. And now we look for prime implicants of size 1, but there aren't any any individual 1 cells that are not already contained within some prime implicant we've already identified. And so therefore, this listing of prime implicants is complete. This is all of the prime implicants for this problem. Now, we want to identify the essential prime implicants. And remember that the way we do this is by first identifying essential 1 cells. Now recall, an essential 1 cell is a 1 cell that is contained within only one prime implicant. So as we begin up here in the upper left hand corner, we ask, is this an essential 1 cell? And the answer is yes, because it is only contained within the prime implicant W prime, Y prime, Z prime. As we move down to this next one, we can clearly see that this one is contained within 2 prime implicants, so it's not essential. Likewise, the same can be said for this one. It is included within 2 prime implicants, so it's not essential. This one as well is included within 2 prime implicants, so it's not essential. The same thing can be said for this 1 cell. It is contained within 2 prime implicants, this one and this one, so it's not essential. What about this 1 cell here? It is also contained within 2 prime implicants, this one and this one, so it's not essential. But the final one down here in the lower right hand corner is contained within only 1 prime implicant, so it is essential. So of those 7 ones that we have in this problem in the Karnaugh map, only 2 are essential. The one in the upper left hand corner and the one in the lower right hand corner. So now we ask ourselves, now that we've identified the essential 1 cells, what are the essential prime implicants? Well, the essential prime implicant that contains this essential 1 cell is W prime, Y prime, Z prime. So that's one of our essential prime implicants. And the prime implicant that contains this essential 1 cell, we can look at our, this is one of the places where these little sketches come in handy. We'd go immediately down here, and we see it's W, X prime, Y. So these are the only 2 essential prime implicants for this problem. And now we're ready to finish this up, and we look at minimal sums. Now this is where you need to pay very close attention. So our function is f, and it's a function of w, x, y, z. So I'll say f of w, x, y, z equals. And as has been stressed repeatedly, when you're looking for the minimal sums, you should begin with what is essential. Just think of the word essential. That is something that must be there. So we'll start with W prime, Y prime, Z prime, or W X prime Y. Now, if we have included those two terms in our expression for f, is that enough to account for everything in f? Well, to answer that question, this is where we return to the shading. So if we have this first term, W prime, Y prime, Z prime, as we can tell from this sketch, that will take care of these two ones in the upper left-hand corner. And then when we look at the second term here, W X prime Y, as this sketch tells us, that takes care of these two cells in the lower right-hand corner. So we can shade them in. They've already been accounted for. But clearly, when you look at the Karnaugh map, you can see that the two terms that we have right here do not account for all of the ones in the Karnaugh map. We have 3 ones that are left unaccounted for. Now remember, our whole goal, the whole purpose of the Karnaugh map procedure is to find minimal sums. So we want to find a sum that contains, that is as compact as possible. It has as few literals as possible, and yet accurately represents this function. So the question is, how can we, what terms need to be added to these two terms? These two terms have to be there because these two prime implicants are essential. But what other prime implicants can be added so that we can account for these remaining 3 ones that have not yet been accounted for? Well, this is the first time where you see the possibility of different options. So one way that we could account for those 3 ones, okay, first of all, let's note there's no way to account for them with just one more term, because we don't have any prime implicant that has those 3 ones in it. All of our prime implicants are size 2, so we're going to need at least 2 more prime implicants to account for those 3 ones. But that could be done in a couple of ways. One way would be to use this prime implicant and this one. That would be 2 prime implicants, and so since each prime implicant has 3 variables in it, you see each one of these prime implicants in this problem has 3 literals. So if we use 2 additional prime implicants, that will be 6 more literals. And again, that first option that I discussed was using this one, and this one. Another option would be to use this one and this one. And another option would be to use this one and this one. So we have several options here, and I want to make sure that you see all of those. So we're going to write f of wxyz I'm going to go ahead and write it 3 times because it looks like there are at least 3 minimal sums in this problem. Now, before I finish that first expression, let me go ahead. Remember, every single minimal sum expression must contain the essential prime implicants. So I'll go ahead and write down W prime, Y prime, Z prime, or W X prime Y here, and W prime, Y prime, Z prime, or W X prime Y there. So we're identifying here, it looks like 3 minimal sums. Each one of them has to start with what's essential. And now let's go ahead and finish. So for the first one, what I'll do, I'll take the first one to be the one that has this prime implicant here, and let's see, if we look, we can quickly identify that that is W prime X Y prime, and then this one here, which is, we can identify that one as well, that's WXZ. So again, we have W prime X Y prime, that's this, as you can see right here, and then we must have this as well, which is WXZ. Now, that's one way. A second way to do this would be to include this prime implicant here and this one. So that's this vertical one is X, Y prime, Z. And the horizontal one here is WXC. And then a final way to account for these three ones would be to have this prime implicant here and this one here. So this one is X, Y prime, Z. And then this one, as we can see over here, is WYZ. And I don't see any other ways to do this, any other expression that would account for all three of these ones would have to be bigger. Notice that all three of these expressions we have have 12 literals. We have 3 literals there, 3 literals there, 3 literals here, and 3 here. Each one of them has 12 literals. So these three expressions are all the same, have the same number of literals, but any other expression that you find, any other sum expression you find, will have more. So this problem, this particular function, has 3 minimal sums. And that's an example of a problem where you have more than one minimal sum, and that's the way that you could handle that. So I hope that makes that concept clear, and I believe that, as I mentioned before, if you were able to do that on your own, you certainly understand the use of Karnaugh maps to find minimal sums. So now let's start a new topic, which is the use of Karnaugh maps to find minimal products. We need an example to work with, so why not work with the problem that we just did? Now, so we'll say find. So for example, find all minimal products of the function f of w, x, y, z equals the sum of the minterms 0, 4, 5, 10, 11, 13, and 15. So, as we've hinted in class already, when we want to use the Karnaugh map to find minimal products, we generally work with the 0 cells in the Karnaugh map rather than the 1 cells. Now we know that min terms correspond to 1 cells, and likewise max terms correspond to 0 cells. So when you're looking for minimal products of a function, it's convenient to have the function written in terms of max terms. That this is not necessary, but it is convenient. So let's go ahead and write this function in terms of max terms. Instead of being equal to the sum of the min terms 0, 4, 5, 10, 11, 13, and 15, we know that it can also be written as the product. Remember, this sign means product. The product of the max terms 1, 2, 3, 6, 7, 8, 9, 12, and 14. Now that we have identified that, you'll see that a lot of this is going to look very, very familiar to you. So we want to we want to find the Karnaugh map for this function. Again, our reasoning is that we have 4 variables, and so therefore we end up with a 4x4 Karnaugh map, because 4 variables gives us 2 to the 4th cells, which is 16 cells, which is a 4x4 Karnaugh map. And again, we'll put the first 2 independent variables on the vertical axis and the last 2 independent variables on the horizontal axis, and we will number just in the usual way. And now we will count off the cells in the usual way as well, but the only difference is, since we're identifying max terms now, we will use zeros rather than ones. So remember, this is cell 0. We don't have 0 in our list of max terms, so we skip that. We get a 0 here in cell 1. Skip over. This is 2, 3. We don't have cell 4. We don't have cell 5. We do have 6 and 7, 8, 9, but we don't have 10, we don't have 11, we do have 12, and we don't have 13, but we do have 14. So if you compare this Karnaugh map to the one that we had before, you can see that they're exactly the same. It's just that because we have zeros where we had blanks before, and we have blanks where we had 1 before. So it's really just the same Karnaugh map. It just depends, the only difference is what we choose to show. And since we're dealing with max terms now, since we're trying to find all minimal products, it's most convenient to show these 0 cells. Now, let's write a note here. When finding minimal sums, we look for prime implicates. Implicants. This is what we've been doing all along. But now, when finding minimal products, we look for prime implicates. And you might be able to guess what these are. Remember, we said that for a prime, well, for an implicant, we said the following. A is an implicant of B means A equals 1 implies B equals 1. Well, similarly, the word implicate is the following. A is an implicate of B means A equals 0 implies B equals 0. And we can look at more examples of that later, but for right now, let's just work with what we have. So we'll begin. We'll write PI again, just as we have been, but now instead of meaning prime implicant, it means prime implicate. So we want to find all prime implicates for this function. And clearly we don't have any rectangular groupings of 16 zero cells. So we now drop down to 8. And now we do have, I guess, 1, 2, 3, 4, 5, 6, 7, 8, 9. We do have 9 zero cells, but we don't have any rectangular groupings of 8 zero cells. And so let's drop down to the next power of 2, which is 4, and ask if we have any rectangular groupings of 4 zero cells. And the answer is yes. You can see that up here in the upper right hand corner we have that grouping. And now we need to figure out what this is going to be equal to. Now, just as before, we want to identify what variables are constant. And we notice that W is constant and equal to 0 over these 4 cells, but X is changing. The value of X on the top row is 0, the value of X on the bottom row is, on the second row is 1. Since X is changing, it will not appear in the name. Since W is not changing, it will appear in the name. And now when you're naming implicates, W equals 0, when something is equal to 0, that's the unprimed variable. So we have W. And remember now, we're not looking for products, we're looking for sums. So it's going to be W ORed with something. And let's see what it gets ORed with. Okay, what about Y and Z? Well, Y, for these 4 cells, Y is constant and equal to 1. But Z is changing. So since Z is changing, it will not be in the name. Y equals 1 means we get Y complement. Now, are there any other rectangular groupings of 4 zero cells? And I believe that the answer to that is no. And so now we'll move down to rectangular groupings of 2 zero cells. And there will be several here, so I'll start with this one up here at the top. I encourage you to try yourselves, since this is a new idea. Try to figure out the name for this rectangular grouping of 2 zero cells, and then we'll do it together. Okay, so we notice that W is constant and equal to 0. Likewise, X is constant and equal to 0. So we'll have W or X. Now y is changing because y is equal to 0 in this cell and y is equal to 1 in this cell, so y does not appear in the name. Z is equal to 1 in both cells, and so we have or z prime. And that takes care of that prime implicate. Another rectangular grouping of 2 0 cells is right here. Now I encourage you to try to figure out the name for that and then come back to the video. So I hope you had luck with that, and let's see what we have. W is changing, so it's not in the name. X is constant and equal to 1, so we have X prime. And what about Y and Z? Well, for these two cells, Y is constant and equal to 1. Z is constant and equal to 0. So we have or Y prime or Z. And now let's identify any other prime implicates. Well, we have this grouping right here. And what is the name of that? W is constant and equal to 1, so we have W prime. X is changing, so it doesn't appear in the name. Y and Z are both constant equal to 0, so we have or Y or Z. And we also have this prime implicate right there. And what is the name of that one? Well, W is constant and equal to 1, so we have W prime. X is constant equal to 0, so we have X. Y is constant and equal to 0, so we have Y. Z is changing, it's equal to 0 in this cell, but it's equal to 1 in this cell, so since Z is changing, it does not appear in the name. Now we look at this, and we ask, okay, is that it? Are those all of the prime implicates with 2 0 cells? And you might be very tempted to say yes, but it's not. Don't forget the tricky ones. One tricky one that we have not yet identified is this one. We have the grouping of this 0 over here on the right hand side with this 0 on the left hand side. So let's identify that. Here we have that and that. There's the sketch. And let's ask ourselves what the name of that prime implicate will be. W and X are both constant. W is constant equal to 1. X is constant equal to 1. So we have W prime or X prime. Now what about Y and Z? Well, Y is equal to 0 in this cell, but 1 in this cell, so Y will not appear in the name. Z is equal to 0 in both cells, so we have or Z. And now we ask, are we now done with all prime implicates of size 2? And the answer is once again no, because we have this 0 down here at the bottom of the second column and this 0 at the top of the second column. So we need to identify that prime implicate as well. And think for a moment to see if you can come up with a name. And if you do, you'll see that W is changing, so it's not in the name. X is constant and equal to 0, so we have X. And Y is constant equal to 0, so we have or Y. And Z is constant and equal to 1, so we have or Z prime. And now we ask ourselves, once again, do we have any rectangular groupings of 2 0 cells that are not completely contained within a single grouping that we've already identified? And now the answer will be no. There are no more groupings. So this listing here of these 7 prime implicates is a complete list of all the prime implicates for this problem. And now we want to identify, just following along very similarly to what we've been doing, we want to identify essential prime implicates. And how do we do that? We do it by first identifying all essential 0 cells. Well, as we go through the Karnaugh map, this is clearly not essential, nor is this, but this is. So we have this is essential, but no other 0 cells in this problem are essential. So we have, of the 9 0 cells that we have, only 2 are essential. And in fact, those 2 0 cells both fall within the same prime implicate, which is this first one that we identified, W or Y prime. So the only essential prime implicate for this problem will be W or Y prime. And now that we have identified that, now we're ready to finish the problem by identifying all the minimal products. Now, just as was the case when we're identifying minimal sums, we must first begin with what's essential. And what is essential is W or Y prime. Now we're doing a product now, so I'll go ahead and put the parentheses around that term. And by including that term, we have accounted for these 4 zeros in the upper right-hand corner, so I'll shade those. And now we want to find the most efficient ways to account for all of the other zeros in the problem. So let's ask ourselves, we see that there are remaining 5 zeros, and let's consider the different ways that we could account for those. Well, if we include this prime implicate, the one that starts here and is continued on the bottom, that will take care of these 2 zeros. So let's go ahead and start thinking along those lines. Now this prime implicate that we've just been talking about, the one that starts here and continues on the bottom, that is this one, X or Y or Z prime. So I'll have X or Y or Z prime. And that would take care now of these 2 zeros. We also need to take care of these 2. And if you think about it, there are a couple of ways you could do that. If you included this one and this one, that would be the prime implicate that it contains those 2 would knock out that, and then you also have the prime implicate here that you could take. And in fact, there are several ways, so let's just go ahead and investigate these. Okay, so now keep in mind, I don't want to shade them in quite yet because we obviously have multiple minimal products in this problem, so I don't want to get things confused. But let's go ahead and see. I took this to begin with, and now based on that choice, let's see what other choices we have. So one would be to take this prime implicate right here in the 3rd row, and that one is W prime or X prime or Z. And now that we have taken those two, the x or y or z prime, which takes care of these two zeros, and the w prime or x prime or z, which takes care of these two zeros, then all we have left is this zero, and it can be taken care of in two different ways. So that means that there will be two minimal products that start off with these three terms. So I'll go ahead and have w, x, y, z equals w or y prime, x or y or z prime, w prime or x prime or z. Now once again, remember that by including these three terms, we are taking care of all of the zeros up above except for this one in the lower left hand corner. And there are two ways to take care of that one. That is by the inclusion of this prime implicate or by the inclusion of this prime implicate. So we'll use the first choice. For the first one, we'll say w prime or y or z for the first one, and here we'll say w prime or x or y. So here are two ways that we could account for all of the zeros in this Karnaugh map. But I believe there might be others as well. So let's try again. We have f of w, x, y, z equals... Now, by the way, in case you're wondering, this problem is a bit more involved than certainly what you should expect on the final exam, because you can see that once you begin to have so many alternatives, it does get sort of complicated. But it doesn't hurt at all to see an example of this worked out. So let's look at still another option. So again, now remember, everything we write down here, every single minimal product we include must have what's essential. So we'll always start off with w or y prime, which will take care of these zeros in the upper right hand corner. And now let's try to think of some alternatives to what we've done already. Well, remember before we included x or y or z prime, so that we would, that's x or y or z prime, that is this term right here. That's the last prime implicate that we found. We included that so that we could get this zero up here. But there's another way that we could get that zero, and that would be through using this prime implicate. So let's try that this time. This prime implicate that we just mentioned right here is w or x or z prime. So I'll put that w or x or z prime. Now once we make that choice of w or x or z prime, which again, if we look at this sketch up here, this will take into account this one extra zero, we see that we still have 4 remaining zeros that need to be accounted for. And remember also that for this term to be minimal, we have to, it can be no longer, it can have no more literals than the 2 previous products we've identified, and therefore it can only have 2 more of the 2-cell prime implicates, and therefore if we choose to have the w or x or z prime, which takes care of this zero, then for the remaining prime implicates we have to choose the one that takes care of these 2, which is w prime or x prime or z. and the one that takes care of these two, which is W prime or X or Y. And now if you look at that, you may think that that is a complete listing, but if you look very carefully, you can find, I believe, one more minimal product. Once again, it must, just as is the case with every minimal product, it must have what's essential, so that's W or Y prime. And let's again return to the idea we had in our first two minimal products. We will include X or Y or Z prime, this one right here, so that we can take care of these two zeros. But now, to take care of this zero, instead of using W prime or X prime or Z, this one right here, we've used in our two previous cases where we started out this way, we used W prime or X prime or Z to take care of this zero, but we know that there is another way of taking care of it, and that is to use X prime or Y prime or Z, as you can see from this sketch. So let's say X prime or Y prime or Z. And then if we do that, okay, now we've accounted for this zero through the inclusion of that term. We've taken care of these two zeros here by including X or Y or Z prime. Now we have two remaining zeros, and they must both be accounted for by this last term, because we, again, this entire expression can be no longer than any of our previous expressions, and so we must take the prime implicate that accounts for these two zeros, which is W prime or Y or Z. And I believe that that is it. If anybody is able to find any other minimal products, definitely write me an email and let me know, or let me know in class so that I can notify everybody else. But I believe that this is it, and I want to make a few comments about our listing here. So we end up concluding that there are 4 minimal products. Note that each one of them has 11 literals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Another thing to note is that the only term that is common to all of these is W or Y prime. It is essential, and it is in every one of these. But X or Y or Z prime is in the first one, the second one, and the fourth one, but not in the third one. W prime or X prime or Z is in the first one and the second one and the third one, but not in the fourth one, and so on. You can check the others, but there is no term that's common to all of those minimal products except for W or Y prime. And finally, I want to remind you once again, if you were not able to identify all of these minimal products, don't feel bad, because this is a particularly complicated problem, but it does give you good practice. On one of our special tests or on the final exam, certainly you should not have to worry about something this complicated. You may have a problem where you will have more than one minimal sum or more than one minimal product, but I certainly don't think that you'll have any with as many as 4. So just treat this as a very good practice. Overall, you can see, though, that the procedure for finding minimal products is very similar to the procedure for finding minimal sums. The only thing that might be tricky to you is the naming of the various prime implicates. And so for lecture 14, we will begin with one more example of using Karnaugh maps to find all minimal products before moving on to another topic. Now let's look at some problems for this lecture. The problems for lecture 13 will be similar to the problems for lecture 12 in that in both cases all of the problems will deal with just one function. So in the case here for lecture 13, we have the function g of w, x, y, z is equal to the product of the max terms 0, 2, 5, 6, 7, 8, 10, 13, 14, and 15. And for 13.1, you're supposed to list all of the prime implicates of this function. And your choices are A, x or z, x prime or z prime, x prime or y prime, B, x or z, and x prime or z prime, and y prime or z, C, x or z, and x prime or z prime, and x prime or y prime, and y prime or z, and finally D, x or y or z, and x prime or z prime, and y prime or z. 13.2, list all essential prime implicates of this function. A is x or y or z, and x prime or z prime, and y prime or z. B is x or z, and x prime or z prime. C is x prime or z prime, and y prime or z. D is x or z, and y prime or z. And then finally, in 13.3, you want to list all minimal products of this function. In A, just one minimal product is given. In B, just one minimal product is given. But in C and D, in both of those cases, two minimal products are given. So you need to decide which choice is correct. And one more thing here, when I listed A here, I didn't say the word and, but of course these commas mean that these are different terms here. So for A, this choice is x or z is one prime implicate, and then x prime or z prime is another prime implicate, and the third one would be x prime or y prime. So anyway, I think that all of that is legible, and it goes along just like the problem or the problems at the end of lecture 12. So that concludes lecture 13, and good luck.